So my lectures are about daily applications of the univalence axiom, and I have to say I kind of stole this title from a colleague who organized once a workshop about daily applications of the univalence axiom, and it was exactly what I was working on because I've been trying to find what are really elementary facts that everybody knows about, but you can somehow find univalence axiom in there, some applications. And what I want to do in these 3 lectures is to show some of those to you. And the plan for today is I will explain you what does Univalent Foundations look like. I'll describe to you more or less in an impressionistic manner what Univalent Foundations is. I'll give you some overview, what are the main themes. And tomorrow and on day 3, I will give some applications in group theory and in combinatorics. The results that I'm gonna talk about are maybe not the most impressive or science advancing kind of results that one could wish to see at the mathematics conference, but they're meant to be instructive insights if you want to use type theory in your teaching or to learn to see actually the univalence axiom is always all around. So that will be the message of my lectures. And I also stole this picture from from a book that some colleagues are writing about the symmetry group theory. I've been formalizing a lot of their stuff in EGDA, and credit goes to them, not to me. I didn't make the picture, but I really liked it. So there it is. It's from the symmetry book by 5 authors. Ulrich Buchholz is in the audience here, and let's get started with introduction. And I want to introduce give some general remarks about type theory, what it is, and why we would do it. So it's a language for all of mathematics. And that's the main reason why we would consider type theory. And it's of course a different language than first order logic or higher order logic that most of us are taught if we are going to math undergrad. But the approach in type theory is much more structural. You don't have to have a separate language for your conversational mathematics and then to have an implementation in your ZFC that then actually looks quite different. In type theory, they actually look quite similar. If you encode your concept into type theory, it kind of is the thing that you are talking about quite literally, instead of some encoding using well-founded sets. So the idea is here that it's a much more structural approach to mathematics. It is very convenient for expressing mathematical concepts. You can be very precise, and we will see also in this first lecture that there are some surprises. If you formulate a concept in type theory, you automatically get the type of all objects that are in that concept. And together with the univalence axiom, that's going to play very nicely. So it's very nice for expressing mathematical concepts, and of course it can be used for both classical and constructive mathematics. And the thing that I didn't put in the slide is that it's used also in formalization, but we're going to get to that. But I think it's quite important, this last point, because there are a lot of people that are interested in type theory are very enthusiastic about constructive mathematics. But a lot of classical mathematicians are much more enthusiastic about classical mathematics. And it's very important to accommodate both. And in type theory, you can of course do that. And we have some examples in the Lean maths library. It's based on type theory, but they use classical mathematics, and they got very far and they're very fast. And in the Calc library, it's constructive, as far as I know, and in ACDA too. Of course, you can assume the axiom of choice there too, but that's not the focus in math libraries in those proof assistants. But you can, and this is super important. Okay, and I'm a homotopy type theorist. My specialty is the Univalent Foundations. So I would also then like to say, okay, this type theory allows for homotopy type theory, and apart from being a language of all mathematics, is also the internal language of infinity toposes. So if you prove anything in in type theory using univalence, perhaps, then it's automatically going to be true in all higher toposes. And this is a result due to Mike Schulman. This leads to, this is for some people really a motivation to try to get some of these theorems into homotopy type theory, just to know that they're true in all infinity toposes. For example, the Freudenthal suspension theorem, but especially in the Hurewicz theorem paper, they mentioned this is our main motivation to pursue the Hurewicz theorem. It's by Dan Christensen and Louis Kokkola, and they want to know that it's true in all infinity toposes, and these are all results that are formalized in homotopy type theory by various people, not by me, and they are true in all infinity toposes. So that's good to know. Type theory, because it's a little bit different than set theory, it can also be used to discover new mathematics. And famously, Voevodsky discovered very new mathematics, namely he discovered the univalence axiom by studying type theory of Koch. But also, because now we're working with the univalence axiom, there's actually a lot of low-hanging fruit, still things that are left to discover. So if you're a young person, it's easy to get into homotopy type theory, get some new results, and that's actually really nice. That's also how I started. So that's cool. Let's move on. Okay, so it's the type theory is used in most basic proof assistants, contrary to ZFC. Let's move a little bit quicker. But why would one want to formalize mathematics at all? And the main reason that people will tell you is, well, it's actually quite fun, and I enjoy doing it. And then once my proof is done, and the computer verifies it, and it gives the green light, and then it's really, really satisfying. And it's like a computer game. So people see it that way, and it's quite addictive. It's one of the best computer games out there. And that's one reason that is for most of us the motivation to do a lot of this. But another reason is we are actually recording all of mathematics, or in the process of recording all of mathematics inside computers, and we're making huge digital libraries which can potentially be searched. And Kevin Buzzard likes to make this point that the digitization of music made a huge change in the music industry, and he is expecting a huge change. He's not predicting which one. For mathematics 2, now that we are now that we're recording all of mathematics inside the computer, and we're teaching mathematics to computers, and his goal is to teach the Langlands program to a computer. But there can be many approaches, and it's quite open. In principle, we can do all of mathematics, and it will be nice to have it recorded and make it searchable. It will be easy to contribute by anyone. It's very democratic, I would say. Those are reasons why I would want to formalize mathematics. It also gives the option to merge kind of formal reasoning and computation. Like 10 years ago, like a computation would be by a program that wasn't formally verified to be correct, and we can now kind of see that these things can come together because they are all happening on a computer. The computer can help when you're formalizing something. It keeps track of all your goals and say what's the next thing that you have to do. So that's helpful. When you do something, it gives you instant feedback, which is also useful. So you can use it for teaching, which is very important. There are courses emerging around the world that are based on formalization. In Ljubljana, we are starting with some lectures on EGDA, and I know that other people are teaching Lean and so on, teaching that stuff to undergrad, and that's quite nice. So this is changing, and anyone can join. That's very important. So there are some libraries. I'll get to mathematics soon. If you want to contribute to any Univalent Foundation library, there's the one in Kokhot. This one has the largest community, so it's probably the most important one for homotopy type theory. There is also cubical EGDA if you want to have a bit more computation rule, and if you don't mind dealing with cubes, which can be hard to learn, but then actually cubical EGDA makes it really easy. So it gives you a nice way into that subject. And they recently announced the computation of Pi4S 3. They formalized it, and it's Zmod 2, the whole thing. So it was quite a very big announcement. And I'm working on the EGDA Unimatch library, which is new. I created it like 2 days ago, but there's already like 70,000 lines of code in there. Because I was merging from different libraries. And I wanted to show you a little bit of that, but I'm not going to do it because I'm not on my own computer. I'm on this computer, and I'm not sure what would happen. I think that is the last part of my introduction. Oops, there we go. Oh no, okay, so I want to tell you a little bit about this EGDA Unimatch library. So it's Univalent mathematics in EGDA.
If you want to show something, you can log into Zoom with your computer.
Ah.
But sometimes it's really important.
Okay, well, let's talk about it after the lecture. I think I can do it like just from the slides today. Okay, so like Kokhot, but also very much like the Lean MATLAB, we are taking a very general approach to mathematics, and we want to accommodate all of it. But our library is in EGDA, and it's not cubical EGDA, but it's the normal version. If you go to this website, unimatch/EGDA Unimatch, the third one, then you'll see the source code, but you'll also get to a web page that has the code in a nicely clickable online version, and you can easily browse it. And in our formalization, usually math libraries have a very structured approach where they have a folder with data, and then inside this folder with data they have folders for each of the type constructors. And we chose a different approach because when we were discussing this option, we immediately saw, okay, this result here, where does it go? Is it going in that folder or in that folder? And you have to make a choice, and there's going to be millions of those choices, and every time you make a choice, you make it more difficult to find something. So we were not quite happy. We made our own version where every file has one concept. It introduces that one concept and does maybe a little bit of basic properties, but then finishes there. And they kind of look like NLab pages. It introduces a new idea, does some properties, and then that's it. It goes to a new file. So it's a different structure of the library. And the dream will be to actually manage it like a wiki online. This would be very nice, I think, for an online mathematics library. Currently, we want to work on group theory in Univalent mathematics. We're formalizing the symmetry book, which is this book I mentioned that had the picture from my title slide. And contributions will also be very welcome in any area of mathematics. So if you would like to contribute, I will be very happy with it. Let's do some math. Okay, so the Univalent Foundations for Mathematics, what is it? So it's an extension of Martin Löf type theory. And I'm not going to give you the rules, but I'm going to tell you what are some of the ingredients. But it extends Martin Löf type theory with things like function extensionality, the univalence axiom, propositional truncation, and depending on who you talk to, a little bit more or a little bit less. So you can say, okay, univalence axiom implies function extensionality, so we don't need to assume that, or you want propositional resizing maybe because we want to study the Dedekind rules, and that just works nicer if you have resizing, or maybe you have someone says, oh no, I really want to do algebraic geometry inside type theory, so I'm going to need all these higher inductive types. So we want to introduce those. But so you can assume those, and all of that fits in univalent mathematics. And because type theory is a language for structural mathematics, we take here a very structural approach to mathematics, and the univalence axiom confirms that. That kind of view, it kind of forces mathematics to be structural. And very important again is it's compatible with both classical and constructive mathematics. So I want to stress that because this is an important point for the wider mathematical community. So the main players in type theory are dependent types. So types are the objects of reasoning in this language, and they can have elements A, B, C, and they can also depend on elements of other types. So you can have families of types that vary over elements of other types, and that's what a dependent type is. And in a proof assistant, what that would look like is you would assume an element X and A, and now I'm going to construct a new type using the free variable X. And then you can construct maybe a type, maybe the type is X equals 0 or something like that, and that's a type that depends on X. So those are dependent types. Roughly, that's the idea at least. Let's see, it is moving, yes. And then you can do things with them. If you have a dependent type, then you can consider the type of all the pairs where the first element of the pair X is an element in your first type, in your base type A, and the second element is an element of the in the family B of x. So for every type family you can make such a pair. This is called the dependent pair type, or sometimes dependent sum, and it kind of behaves like a disjoint union if you think of types as sets. But if you think of types as spaces in the homotopy interpretation, then this will be the total space of a fibration, and the type family would be a fibration. Okay, and the other very general thing that you can do is if you have a type family over A, then you can look at the sections of that type family. So how do you choose for every x in A, one point in the fiber over that point? And these will be functions of which the output depends on the inputs, and that's why we call them dependent functions. And you can make the type of all of them. And the pi type, as we often call it, consists of functions of the form lambda x f of x. I'm not saying that all of them are definitionally equal to this, but these are still what makes the pi type work. Okay, and the characteristic ingredient of Martin-Löf's intentional type theory is the identity type, because his idea is, okay, we have the sigma type, and we can read it as an existential quantification, and we have the pi type, we can read it as a universal quantification, and we also have products that we can read as conjunction, and coproducts that we can read as disjunction, and then one of the other important things that we have in logic is equality. We can express equality. It's a proposition usually, but in our system we don't have a separate layer of propositions. We only have type theory, and all the things that we express it as types. So we're going to introduce the identity type as a type. So what this means is that for every x and y in A, we're going to have a type of identifications from x to y. That's this x equals y. It's not a proposition, but it's a type now. And to prove equality, you're going to construct an element of the type x equals A. So that's the idea. And then it's not just any type, it's inductively generated by one element, namely raffle from x to x, or rather a family of elements, because you have this for every x. And the induction principle, it could be like a little bit tricky to see why that makes sense. But the induction principle always says if I have some property that depends on elements of my inductive type, an induction principle asserts what you have to do to prove your property for all the elements. So here it says, what do I have to do to prove property for all identifications? And because the inductive type has only is generated by one element, it says, okay, you only have to do it for that one element, namely you have to prove your property for raffle. But now the property, because we're in type theory, is expressed as a type family. And the type family is going to take a variable of A, y and A, and then it's going to take an identification. I call it E here. E is an equality from x to y. It's an element of that type, x equals y. And it tells me what do I have to do to prove P of ye for every y and for every e. And it says you only have to, does this work? You only have to prove P for raffle, x raffle, and then you get P for every y and e. So that's what this is saying. So it's kind of just a straightforward rule, but it has some, it allows for the possibility of homotopy type theory, and this is quite interesting that this is possible. So that's the identity type. And using induction, you can then construct a groupoidal structure of every type. So think it was Benno van den Berg and maybe Peter Lumsteen who showed that every type has the structure of a weak infinity groupoid, and that uses this induction on equality. So let's do the first two steps here. If we have an identification P from X to Y, how do you invert it? So we want to construct P inverse from Y to X. Well, we look at the induction principle again. We want to construct an equality from Y to X. And the induction says, okay, we have to do that for every Y and every P. And the J rule says, okay, if you want to have something of this shape, you only have to do it for Raffle. But this type, in the case Raffle, X Raffle, it changes the Y to an X, but it didn't depend on Raffle, so you don't see that here. So this is PX Raffle, and it implies there. So if you look at J Raffle, then we get this function, and it inverts this P. So that's how that goes. And you can also use this to concatenate two paths with two identifications. So in the beginning of homotopy type theory, we would call these identifications, we would call them paths because this was our interpretation, right? We thought of types as homotopy types or spaces, and then the equalities would be paths. But maybe there are other interpretations, so now we prefer to call them identifications again. And in the homotopy interpretation, it's fine to call them paths, but in general, you would just call them identifications. Okay, so we want to concatenate them. How do you do that? Okay, so you make your type family over an arbitrary path again. The type family here says, okay, we want the functions from Y, identifications from Y to Z to identifications from X to Z. And to prove that there is such a function for every Y and P, by the J rule, you only have to do it for Y equals X and P is Raffle, but if Y is X, then we get this function, and here we take the identity function, and that gives us an element of this type, and that gives us the concatenations. And then you can continue in similar fashion to prove associativity. You can prove a MacLane pentagon. You can do the Ekman-Hilton argument to show that the second loop space is not contractible, commutative, and so on. You can prove all the laws. So that's very nice. Then on to homotopies. A homotopy for us is a pointwise equality. So we take a function f from A to B, or more generally, you could make this a dependent function, but just for simplicity, I wrote here a non-dependent function. And then I miss here a G. I'm also assuming a G from A to B. And then the type of homotopies from F to G is just the type of pointwise identifications between the values of F and the values of G. Okay, so now we have a notion of homotopies. We can say what it means to be a section of a map, and the type of sections. So here you start to see this idea. We express a concept and we immediately get the type of all of those things. So to be a section, we give a map in the reverse direction from B to A, and we give a homotopy from F composed G to identity. And the type of all of these is the type of all sections. And the same for retraction, but now the G is a left inverse of F. And when you put these two together, you get the type of is equiv of F. So is equiv F is the product of the type of sections of F and the type of retractions of F. This was not Voevodsky's original definition, but André Joyal suggested that this is a good definition of equivalences. And the reason is that it only uses homotopies at one level. It doesn't use any higher coherences, but it still is a proposition, as we will see later. And now, now that we have defined what it means to be an equivalence, you can also define the type of all equivalences, and you do that with sigma. The type of all equivalences consists of functions that are equivalences. So that's how you read this. And now that we have equivalences, we can go to universes and express the univalence axiom. So a universe in type theory is a type. I didn't write here that it's a type, but U is supposed to be a type that is closed under all the type constructors, pi, sigma. Equality is a type. Cartesian product, coproduct, and so on. And why would we be interested in having universes? It's going to be useful for one reason, is that dependent types over any type are maps from that type into the universe, at least the small dependent types. But we can also use this to express structured types, such as the type of pointer types, or we can define the type of all groups, we can define the type of all rings, all spectra, and so on. So universes are useful for that. And one thing in type theory is we are always interested in, for all of these type constructors, we always want to know what is equality of that type. So the one we can't say anything about is equality of equality. That's just what it is. But we can characterize all of the others. So we can say what is the equality of a pi type is going to be equivalent to the type of homotopies. That's function extensionality. Equality of the type of dependent pairs is going to be some kind of a dependent pair construction, and so on. We are always characterizing equality. And the univalence axiom does that for the universe. It answers the question, what does it mean for two types to be equal? And of course, in mathematics we learn that we cannot really distinguish between any two isomorphic objects. The differences that you can make between isomorphic objects is, well, how is it constructed in ZFC? Maybe it contains the element 3 and the other one doesn't, but that kind of difference is insignificant. It's non-structural, if you want to say. And in homotopy type theory and Univalent Foundations, we say, okay, no, actually we never have to bother with that. And we just say that isomorphic things are equal as an axiom. This is consistent. So in set theory it would be inconsistent, but in type theory it is consistent to have that. And we can actually make our formal system compatible with informal mathematical practice that way. And this is one reason why one would consider Univalent Foundations. Is it tries to match with the mathematical practice. So it says that this map that you can define from the identifications from A to B to the equivalence from A to B, that this map is an equivalence. And this is what we will give daily applications of. I have 20 minutes more. 15? Okay. Good luck to me. So the next concept is contractible types. What does it mean for a type to be contractible? Is you can construct an element of it. This will be the center of contraction. And then you can prove that every element is equal to that one. Sorry?
I said 50, not 15, right?
50, 50? Yeah. Ah, I have a lot of time. Oh my God. Okay, well. Okay, I was stressing for nothing. Okay. Okay. So, well, in that case, are there any questions so far? it's a good time to ask. Yes.
Could you elaborate on that result by Schulman, where he says that homotopy type theory is the internal language of infinity typos?
Oh yeah. Okay. So it's a bit analogous to the result for one topos, where you can say, okay, we have the Mitchell-Benabou language of a one topos, and if you prove something in that language, then it's going to be true for all toposes. And this is result in that spirit. So here, what Schulman proves is that okay, you have type theory. It has certain syntactic rules that I didn't show you at all today, because syntax is very difficult to define precisely, as many people will appreciate. And then you can then you have semantics. So if you define a syntax, ideally you would have a good semantics for it. And here in type theory, the way it started out, the semantics was constructive set theory. But then, of course, in the 90s, they discovered that you cannot prove the uniqueness of identity proofs, which I didn't discuss here today. So this wasn't the complete semantics, and then Voevodsky discovered the univalence axiom, and along with the univalence axiom, he immediately constructed a model for his axiom, and this model was in simplicial sets. And he did this by saying, okay, the dependent types are the Kant vibrations, and sigma is the total space, and the identity types are the one cells, and the pi types you can make a Kant simplex of continuous sections and so on. So he gave interpretations of all of the ingredients of type theory, and showed that, okay, indeed univalence axiom holds. So there are some models, but then of course the simplicial sets form an infinity topos. The whole Lurie's book is based on simplicial sets, and the question immediately is, okay, can we generalize Voevodsky's simplicial model of type theory? And Mike Schulman answered this question finally in 2019, I think, that yes, you can. There are a lot of technicalities to make universes closed under all of these type constructors, I believe, and while at the same time they should remain Kant complexes, the universes itself, or at least vibrant. Sorry, I should say vibrant. Yeah, it's a long technical work. Did I answer your question? Okay.
Yeah, pretty much. Thank you. I
Oh.
just wanted to know if it was relatively new.
Yeah, it's from 2 years ago, I think. Yeah. Yeah, and the other semantics is due to Cherry and collaborators about a cubical approach to ACTA, and in this one you can prove constructively that it models univalence, and this is also very important. This is why we say that Univalent Foundations is compatible with both constructive mathematics and with classical mathematics. Okay, any more? Yes?
Is a notion of contractibility. Semantically is essentially saying that the home from X to Y is contractible. I mean, it is equivalent to the slice over Y in some sense, in some semantics.
You're talking about this element Y here?
Yeah.
Oh, okay. Yeah, okay, so what you're saying is you think as a groupoid. Groupoids are categories, so we can think of them as categories, and then this is the homomorphisms from X to Y. Okay, so in this definition, Y is in the other position, so we co-slice, but kind of. I think I wouldn't advise thinking like that, but maybe you can. The best way to think about this is just there's the space of all points, and then this one is a homotopy from the constant function that always gives value x to the identity function. So it's the homotopy from the constant function to the identity function. So it's this it's a contraction, but it's going the other way around in this formulation, and these are continuous sections. So this is not just path connectedness, but it actually is corresponding to contractible. And you can prove that the type is contractible if and only if it's equivalent to the terminal object, to the unit type. Is that okay as an answer? Yeah. Okay, cool. Okay, and then there's this important observation that you can make about contractible types and equivalences, is that every map from A to B is an equivalence if and only if all the fibers are contractible, and the fibers are like the pre-image in type theory. So the fiber of f at B consists of all the points in A that map to B, and you express this as a sigma type. So all the points in A such that, and whenever you see this statement in informal mathematics, you think, sigma type. Such that means sigma. So every element in A, so the elements in A such that f of x is B. What this means is that if these are all contractible, it means that f is a one-to-one correspondence, that there is only one thing in the pre-image, but there's exactly one thing in the pre-image that maps to it. Whereas being an equivalence is more like the categorical idea of being an isomorphism. It has a left inverse and a right inverse. So we just make the distinction to make these inverses separate, but other than that, it's kind of a categorical idea. And of course, set theory, you can prove that function has a left inverse and a right inverse if and only if it's a bijection. In type theory, it's a little bit harder, but you can still do it. When you do this proof, so we're not going to do it now, you'll see that you have some higher coherence to deal with, and you can indeed manage it. So this is a theorem. And also I should say, this was the notion of maps of which the fibers are contractible. That was Voevodsky's original definition of an equivalence. So he formulated the univalence axiom with this notion where the fibers of F are contractible. And why did he do that? Why don't we just say that a map is an equivalence if it has an inverse, the way we used to? That was because he was aware that that there might be some coherence issues if you just say that the map a map has an inverse, and it's hard to point down. But if you just say contractible, you kind of know that you're safe. So that's kind of one reason. There's nothing in this type except that the point and all of the rest is equal to that point. There can be no funny loops because you can prove that those are raffle. So it was a safe choice, and then André Joël came along and said that okay, isomorphisms are kind of wrong, but if you make the left inverse and the right inverse separate, like in this definition of equivalences, we take the product of the sections and the retractions, then it's cool again. It's safe to you won't run into problems, and the reason is that if a map is an equivalence, then the type of sections is going to be contractible, and also the type of retractions is going to be contractible. So this type is going to be contractible, and that's why why being an equivalence is a property. So you start noticing that now I'm starting to talk about properties and being careful about coherence. I'm gonna get more and more into that. But I kind of hope that you get it by osmosis rather than me giving a definition. But the definition of property is going to come later. But you can always raise your hand and ask me to clarify something. So now I have 50 minutes left, or 40. Okay. And I was already saying this before, but in homotopy type theory, the kind of thing that we do daily is to look at a type and say what is its identity type. We always want to know what is the identity type of this. We want to understand it as good as we can. And to answer such questions we have a theorem that I like to call the fundamental theorem of identity types. And its purpose is to help you with saying, with characterizing the identity type of any given type. And the way it works is this. You start with a type and it has an element. And then we want to say the identity type of identifications from A to X. We kind of want to make an educated guess. It should be equivalent to B of X. So we make up some type B of X that we kind of make, I guess, we can guess, or we read it off from what A is. And we want to prove as the goal that B of X is equivalent to the identifications from A equals X. And the theorem says what you have to do to make such a proof. And it does so by stating an equivalence. So it says that any family of maps from the identifications to B of X is a family of equivalences. So that means that each of these is an equivalence. And note that there is always one map like that because we assumed B in BA. So we can send Raffle to B and get a family of maps like that. But this works for any. And that's the case if and only if the total space of all B's is contractible. So that's a good theorem to have because now we know how to characterize the identity type of A. It's by showing that the total space of a B is contractible, and this corresponds to a familiar fact in homotopy theory, where the total space of the path vibration is a contractible space. So it's exactly like that. But this one gets used over and over again in homotopy type theory, so we call it the fundamental theorem for that reason. Okay. I already started talking about properties. So here's the definition of a proposition. A proposition is a type of which the identity types are contractible. So the way to say that is just with the pi type for every x and for every y is contour the type of identifications x equals y. So is contour here is that sigma pi thing that I had on the other slide. And then you can define prop to be the type of all propositions in U. So here you see the universe is really useful. We can also make a universe of propositions by looking at this sigma type. And is-equiv is always a proposition. That's because, like I said, if you know that the map is an equivalence, then you can prove that the type of retraction and the type of sections are both contractible. Also, being contractible is a proposition, and being a proposition is a proposition. So this is quite different than first-order logic, where, of course, to be a proposition is not itself a proposition. But this is very important because if we take a sigma type and the family we do sigma with is a family of propositions, then the equality in the sigma type is going to be the equality in the underlying type. So that's the case here. Yeah.
When you say it comes equipped with an element, it means that that type that we define is inhabited?
Yeah, it means that we have an element of this type.
Okay.
Yeah. Yeah, this is something we like to say in type theory, that a type comes equipped with an element of some other type to say that it satisfies that property, but it doesn't, what we express there doesn't always have to be a property. So in this case it is, but it just has an extra element of that type. Or if you would assume that that A is a proposition, then part of your assumption would be an element of this type, which you can then use later in your reasoning to apply to get some later result. Yeah, and come equipped with is usually expressed with structure. So if we assume that A is a type that comes equipped with an element of this type, that's the same thing as we assume an element of such a sigma type. So it kind of is a cue that says we're using sigma types here. Okay, and more generally than propositions and contractible types is the notion of all truncated types. Note that in the definition of propositions, we said the identity types of proposition must be contractible. And now we can say, okay, the identity types must be proposition. What condition is that good for? And here we say, okay, in set theory, the equality is a proposition always because it lands in the proposition. It's not constructed as a set. So we say in type theory that the type is a set if its identity types are propositions. And then you can go on inductively, say that the type is -2 truncated if it's contractible, and it's n+1 truncated if its identity types are all n truncated. So this gives us a whole hierarchy of types that starts at the very bottom below ground, 2 levels below ground with the contractible types. Then there's a layer of logic at level -1 that contains all the propositions. You can do universal existential quantification there and so on. You can do all of logic. Then the 0 level, ground level, is the level of sets. That's where we do most of our mathematics. And so when we're discussing groups, the underlying type of a group will be a set, usually. And then we can do things like Brave New Algebra or something like that, where the underlying types don't need to be sets, but they can be higher up or completely untruncated. There are definitely types that are not truncated for any n, such as the 2-sphere has infinitely many non-trivial homotopy groups, so it won't be truncated for any n. So those types are perhaps the most common, but at least this gives us some kind of hierarchy. And then, very important in the Univalent Foundations, that will help us a lot to express concepts correctly, is the truncation operation. We'll get to expressing concept with this, but first let's see what this is. For any type A, there is an n-truncated type that we write like this, and this n-truncation, you should think of it as left adjoint to the inclusion of all the n-truncated types into all the types. So there is an equivalence here, so I'm saying is an equivalence with the left adjoint on the left and the inclusion of the untruncated types on the right, which we don't notate. So the universal property is the universal property of that left adjoint. It says that this map from the untruncation into an arbitrary untruncated type X, if I precompose that with my structure map eta, this is the unit of the adjunction, then I get another map, and that from A to X, and this map here between these two function spaces should be an equivalence. What that means is that for every map from A to X, I can find a unique map from the truncation of A to X that composes to that one. So for every f from A to X, I can find a unique map from the intruncation of A to X, such that if I precompose with eta, then I get f back. That's packaged up in this equivalence. And the X here is an untruncated type. So the important special case is the propositional truncation, which is -1 truncation, because propositions are the -1 truncated types. And this case is so important that we drop this -1 from the notation and simply write this double bars A without any number here. So when I write this, it means propositional truncation of A. And because this should be a proposition, we can ask, okay, what does that proposition say? And it says that the type is inhabited without giving you any element of the type, potentially. So this is the inhabitedness proposition. And that's very useful because often we want to say that the type is inhabited without actually destroying structure of what we are about to say. Yes?
Out of interest, can you prove that this diagram commutes just from knowing that the map above is an equivalence, or is this extra?
No, this is the condition, and this is explanation of that condition. So you can prove that this triangle commutes
just
from the equivalence. Yeah. Oopsies. Yeah. So if you know that this map is an equivalence, what you know is that, okay, if I start with an f here, then the type of g's that maps to f is contractible, but the fact that it maps to f, so the fact that it's in the fiber, is part of the data there. So if we look at the definition of fiber here, we have something in the domain. So now this is the map G, but we also have the identification as part of our data. So that's where you get the commutativity of the triangle from. Any more? And we move on. Okay. So I promised you can use this propositional truncation to define concepts correctly, and this is very important. It's kind of a new approach, but when we say that a type is finite or a set is finite, usually we don't mean that it's actually that there is a given bijection to a standard finite type, because what that would do is it would also equip your finite type with an order, and usually when we say that a type is finite, that ordering that you would get from the equivalence shouldn't be part of the structure. So the equivalence to a standard finite type shouldn't be part of the structure if you say what it means for a type to be finite, and that's why. Okay, we introduce the standard finite type. Sorry, I went a little bit ahead of myself. The standard finite types are defined inductively. Fin0 is empty, and fin n plus 1 is fin n plus 1. And a type is said to be finite if we can construct a natural number and we can find an equivalence from fin n to A, but we truncate this because we don't want this equivalence to be part of the data. Because if we would do that, then we would get the ordering on A, and of course it's sometimes nice to have that your A is actually equivalent to fin n, but you might just work with fin n then, and that's what most computer programmers do. But we actually want to reason about the concept of being finite. This is a nice thing to do, and we'll see some of that. Oops, this sigma type didn't render properly. The x in u should go to the bottom here. So we define the type of all finite types. I use the Blackboard bold F for that. It's the type of all x in u such that the property is finite holes. And this thing is a property. So there is at most one natural number for which there is such a mere equivalence. Yeah.
Does sigma generally preserve propositions?
Sigma preserves proposition. Okay. So if you take a sigma of a base type A, which is a proposition, and then the family is proposition again. If we would do that, then we get for sure a proposition. But sigma usually represents subtypes. Sigma of a family of propositions is a subtype. So here we have an example of that. It's the subtype of all natural numbers for which there is a proof that A has that cardinality. So if you see a sigma and a property here, then it's kind of analogous to this set comprehension where you, if I can find a chalk, well, it's the bracket notation for sets. I don't find the chalk. There it is. Okay. So if we would have something like this, sigma a bit bigger, x in a p of x, where p is a property, this would be the interpretation of such a thing into set theory would be this x in a such that p of x holds. So when you see sigma like that, you can think of it like this. Any more? Yes.
Could you just explain what the difference between the non-bold and the bold one is on the top?
Oh, yeah, okay. So this one is a natural number. So here I'm talking about the natural number 1. Yeah. But fin n is a type. So this is a coproduct. So this plus is the plus of the natural numbers, and this plus is the coproduct. And this bold 1 is the terminal type.
Oh, I see.
So it's the type with one element.
Yeah.
Yeah. Good question. Any more? Okay. So the n element types now. Let's see. So if we look back at the definition, we say that the type has n elements if it's merely equivalent to fin n. And that means that, that we want it to be equivalent to fin n, but we don't want the witness. So that's this truncation, propositional truncation. So if we can find the element of this proposition. And this is, of course, not equivalent to it being equivalent to fin n. And now we can define the type of all n elements types. And we write BSN for that. And BSN is the type, the sigma again, of all x and u that have n elements. And why do we call the type of all n element types, which in set theory would just be a very large collection of types, of sets, wouldn't have anything to do with BSN. Why do we call it like that? And that's because of this theorem. If we take the loop space of BSN, the loop space of a type at the point A means the type of self-identifications from A to A, and this can be non-trivial type, even though we write it with equality. So the type of self-identifications of the base point of BSN, the base point is this fin n, is equivalent to the type of automorphisms of fin n. And the automorphisms, of course, they are the permutations, and that's why we call this type BSN. One way of thinking about this is that this type is automatically a groupoid with the identifications. By the univalence axiom, the identifications in this type are the equivalences between those two types. We're going to see the proof, but I'm going to explain the idea first. And because this is kind of, you shouldn't think of this as the set or the class of all n-element types, but the groupoid of all n-element types. That is equivalent to the groupoid that has one point and the permutation group of n elements. So that's why we call this BSN. And this works with the univalence axiom. So this is my first daily application. is to prove this theorem that loop space is equivalent to the automorphisms. And to do that, we are going to use the fundamental theorem. Remember, the fundamental theorem had this type A in it. We wanted to characterize the identity type of A, so we had this B, which supposedly characterizes B, the identity type of A. And then it tells us what we have to do, namely prove the total space of B is contractible. So here our family of types is given an n-element type. Oh, I wrote is finite here, but this should be merely equivalent to fin n, so that's a typo. Given an n-element type, we want to say that the identifications from xh to the standard n-element type is the type of equivalences from fin n to x. Sorry about this typo. So this is here our B from the fundamental theorem. And then the goal is to prove that this is contractible. And if we do that, then we're done. Then we get our theorem, because now also the type of identifications from, if we take x to be fin n, that's why we will apply this to, where x is fin n, it will give that this is the identifications on fin n to itself is equivalent to fin n to fin n. Okay. So that's why we apply the fundamental theorem. But of course, if we can rewrite this sigma, and again I made this typo where I say it's finite here, but I should have said that it has n elements, which means that this truncated equivalence from fin n to x. Anyway, so what goes on in this step? So I claim that this type is equivalent to that type is this is a sigma of a sigma and then something. And I can reassociate and put this component to the outside and this component to the inside. So that's just manipulating the order in which I take the sigma. So okay, there's a little type theoretic manipulation. But once I do that, then I can say, okay, here I have the total space of x in U, such that fin n is equivalent to x. That's contractible because I know by the univalence axiom this is the identifications from fin n to x. And then once I have that, I'm left with is finite x here. But okay, so I'm just going to go with is finite x. If I know that if I know that x is equivalent to fin n, then of course it's finite. So this proposition is true, and any true proposition is contractible. So I have here a sigma of contractible types. That's the observation. Base type is contractible. This family is a family of contractible types. So, so if we take sigma of contractible by contractible, we get something contractible. So that's why this works. Any questions about that?
Did you say there's a typo somewhere, or is it okay?
Yeah, so the typo is that this is finite on this whole slide. Should be this proposition. It should say that fin n is equivalent to A. So throughout this slide, I should always say.
So the two things should be the same.
Sorry.
I say one's not truncated. Okay.
Yeah. No, so this is finite. It is the proposition that there exists a natural number such that fin n is A. And here we already assumed some natural number, and we want to say it has that cardinality. The condition is finite is it has some cardinality, and here you want to say it has cardinality n. So it's a slight difference, not a big difference. Yeah. Okay. So that's the first application of the univalence axiom. Is we proved that BSN is deserving its name. It really is a delooping of the end permutation group. And then this theorem, so there are some corollaries of this thing. And this is an observation I learned from Ulrich, but he said this morning, you can attribute it to me, but it really is a really simple thing. It's the groupoid of all pointed n+1 element types is equivalent to the groupoid of all n element types. So this again uses some univalence in the background. And the way that proofs goes is says, okay, if I have an n+1 element type X with a proof that it has n+1 elements, and I have a point in it, so I have a pointed n+1 element type, then what I can do is I can take the complement or the points away from X. So I take the type of all Y's that are not X, and that's now an n-element type, and even more, it's the unique n-element type. X is the unique pointed type that can be written as the complement of X plus 1, where this unit type here is representing X. So this is something I kind of leave it as an exercise, but if you think of this in terms of groupoids, it's kind of clear. The groupoid of pointed n+1 element group sets is equivalent to the groupoid of n element sets, and it goes by complements. But that's like a nice exercise if someone just learns about univalence axiom for the first time. You can give it to them and give them something to practice with that everybody is very familiar with, but it uses the univalence axiom. So that's the kind of the point of this. What this also means is that the groupoid of finite sets is equivalent to the groupoid of pointed finite sets. That's just if I take the take all of these together for every n. So that's a corollary. It also means that the type of pointed two-element sets is equivalent to the groupoid of all the one-element sets, but that's a contractible groupoid because there's only one element set up to equivalence. So this is nice again, because here we are in the situation of the fundamental theorem. And the fundamental theorem says, if I have some type family and it has a contractible total space, then it's the identity type. So what we learn here is that an identification in BS2 from fin2 to X, that's the same thing as giving an element in X. So if you think about this, what do you have to do to construct an identification from fin2 to an arbitrary two-element set is you have to say where the base point of the two-element set goes. So where, let's say they are true and false, or 0 and 1, maybe. Then I have to, if I say where 0 goes, then I know where 1 should go because the set has only 2 elements. So that's kind of very elementary application again. And the type of all equivalences from fin2 to x is equivalent to x. Yeah, that's what we use there. But perhaps surprisingly, this means that we have a family of inhabited types that has no section. And this is a very important point because it seems to contradict the axiom of choice. Here, if x is a two-element type, then x is of course inhabited because it has 2 elements. So it's even twice inhabited. But I cannot prove that there's a function that takes an arbitrary 2-element type and constructs an element of it. This cannot be done. And the reason why it cannot be done is that, well, if we had such a function, we just showed that this one here, x, is equivalent to the equivalences from fin2 to x. So we use that equivalence to say, okay, we have such a function, then we get an equivalence for every x from fin2 to x. But the type of equivalences by univalence is the type of identifications. So this would mean we would have a contraction of BS2. But BS2 should not be a contractible groupoid because it's, it has Z2 in the loop space. So the reasoning here is, okay, from this we get a contraction, but BS2 cannot be contractible because identity types of contractible types are contractible. This is a fact that I'm just telling you now. But the identity types of BS2 are 2-element types. They're not contractible. So that's the contradiction. So there can be no such function. So this means you have to be a little bit careful with how you assume the axiom of choice. And when you think about it, the axiom of choice was invented for set theory, not for type theory, but for set theory. So it's an axiom about sets and not about all types. So we restrict the axiom of choice. The axiom of choice, it says, if I know that every B of x is inhabited, then the type of sections of B is inhabited. And this is true if A is, sorry, I misspoke. This is consistent if we assume that A is a set and B is a family of sets. But if A is a groupoid, then already we saw in the previous example that there are counterexamples. And that's just because if you have a proper groupoid, then as you go around an isomorphism, you can twist. And by this twist, we kind of force to drop the axiom of choice for groupoids. And we only, as a result, we only formulate it for sets. But this version of the axiom of choice, when we restrict it to sets, it holds in the simplicial model of Vygotsky, so it is consistent with univalence and all is good there. So it's compatible with classical mathematics. So this, oh, okay. How much time do I have left now? Sorry? 3 minutes. Okay. I was gonna do some synthetic homotopy theory, and I think I have like 10 slides left. Oops. Let's try. Okay. So now we have just discussed the foundations. We have discussed the main ingredients, the univalence axiom, propositional truncation, how you express finite sets. We also want to do some cool mathematics. So the idea here is, can we construct real projective spaces in type theory? And And of course you can kind of think, okay, there should be lines in an Rn. But we want to construct the homotopy types of the real projective spaces. And what we do to get these is we look at this BS2 again and say, aha, this is the homotopy type of RP infinity, because RP infinity has one fundamental group, which is Z2, and it has no higher homotopy groups. And this BS2 also has nicely the tautological bundle immediately, because if I have a two-element type, then the bundle just gives me that two-element type. So it really is a tautological bundle. So we take BS2 as our model for RP infinity, and now we want to construct by induction RPn out of this. And how do you do this? You say, okay, RP0, that's going to be contractible, because in R1 there's only one line. Of course this has the canonical tautological bundle. And RPn plus 1, to do that is, okay, we go from Rn, we know that by assumption we have the tautological bundle, which is a map into RP infinity, because that one classifies all the line bundles. We pull this back along 1, and now of this pullback we form the push-out. And by the universal property of the push-out, this has a map into RP infinity again. And it turns out that that's a good definition of RPn plus 1. So let me not bother you with why this is the case. There's a descent theorem which I would have loved to explain to you. Yeah, I think the slides will be online, so you can look at this. What you can do for this RPN is construct the usual fiber sequence that has total space Sn, and the fibers are fin2. And this fiber sequence is just a vibration of antipodal points on Sn. So this is something you can prove using the descent property from higher topos theory, which is true in Univalent Foundations. And I think I'll stop here then.
Are there questions or comments? And you should wait for the microphone for the question. Also questions online.
This one. Yeah.
Hello, thank you for your talk. So I was wondering, do we have more context about the introduction of the univalence axiom? Do we know what particular example was Wojcicki considering when he introduced it? Because for me it seems like the univalence axiom come out of thin air, and then a posteriori it's a good axiom, but it seemed like a mysterious thing to introduce at first.
Yeah, so I think that so I cannot speak for Vladimir, but I think he already had some intuition about simplicial sets, why something like the univalence axiom must have been true there, and he was really thinking of type theory as a kind of homotopy theory, or at least this started happening, where a type family is a vibration, and this question about what is the identity type of this type or that type is very important. So it's kind of natural to ask that about the universe, yeah, this seemed to be a good answer, and then he went on to find the model of it in simplicial sets. So I think it comes from his work on simplicial sets, maybe. Yeah. There's one.
Hello. So you talk about the axiom of choice, and in the hot books there is another variant which is AC infinity.
Oh yeah.
So maybe can you talk about this and how it relates to what you've said?
Yeah. Okay. So AC infinity is the property that pi distributes over sigma. So if I have a dependent function and the values are pairs, then this is the same thing as giving two dependent functions. One which maps to the first component and one which maps to the second component. And this is an equivalence which is kind of tautological, and it says pi distributes over sigma. And for a long time, when you interpret everything via the Curry-Howard isomorphism, all of logic, so you interpret universal quantification as pi, you interpret existential quantification as sigma, then one form of the axiom of choice will be the interpretation that pi distributes over sigma. So it is a Curry-Howard version of the axiom of choice. But now we made a change. We don't interpret logic as types, but we interpret propositions as types that we call propositions, the ones that have the identity types propositions. So this changes the interpretation of the logic, and then if you want to interpret sigma, you'll see that you have to use propositional truncation to force the interpretation to be a proposition. And that's where it starts happening, where the axiom of choice now kind of becomes, if I have a family of inhabited sets, I want to have a section of it. That's where a little bit of trouble starts if you are not careful about your groupoids, so you have to restrict to sets. But yeah, it's about different interpretations of logic into type theory.
In any case, it can prove from the rules of type theory.
No, you have to use function extensionality. So there's one postulate you have to make. But other than that, you can prove it. Jerry looks thoughtful. Did I make a mistake?
One last question.
Yeah, from BSN,
Yes.
one can obtain a stable homotopy of spheres by Canpredi. Has any part of this being formalized?
There's a big effort by Floris van Doorn. He constructed pre-spectra and spectra, and then he went on to formalize the Serre spectral sequence. The sphere spectrum, so we can construct suspension pre-spectra, we like to call them pre-spectra, and spectra when the loop spaces are equivalent to the, so the type is equivalent to the next loop space. This has some annoying technicalities which we haven't managed to put in a proof assistant yet, but in principle we can do all of this in type theory. And then, because this gets so technical, you can also look at it from a more synthetic perspective. What is the topos of parameterized spectra? And you can kind of try to characterize it from a categorical point of view, and see what kind of adjunctions are there on this spectra that kind of tell me more or characterize the category of parameterized spectra. And this is work by Eric Finster and some collaborators who have said, okay, we want to have this and these modalities, and if we have those, then we can model parameterized spectra, and we can do it entirely synthetically, just using category theory and a few adjunctions.
Thank you.
Yeah.
Okay, thank you, Egbert.
Thank you.